Hi, this is Rob Carter at piezo.com, welcoming you to our way out introduction to piezo damping. When you're first learning something, it's very important to build up an intuition. And sometimes a simple, outrageous example is really the best way to understand the new subject. Something that's easily visualized, it's on a scale of everyday things that you can relate to, only requires mental arithmetic, and an example that you can carry all the way through to the end. So here's the setup for our piezo damping intuition booster. There is imagine a piezo plank that is 1 meter long and 10 centimeters by 10 centimeters in cross section. And it is supported at each end by these triangular blocks that you see. And in the middle of that plank, there is a 1,010-pound weight. It supports 1,000 pounds of weight. And so what we're going to do is shake that beam, grabbing it by the two ends, up and down. And we're going to see what kind of response that beam and that weight has to that shaking and what we can do about it with the piezo ceramic. Now, I told you that this was an outrageous example. And because of that, we're not going to make that beam. In fact, I'm pretty sure no such beam has ever been made. It weighs 172 pounds for one thing. So where are you going to put it? So in lieu of the experiment, we are going to resort to using a finite element model to explore what such a beam might do and build up our intuition. So here's a picture of that finite element model. You can see the purple bar is the piezo beam. There are two layers to this, a top layer and a bottom layer. This is a bimorph type configuration. And those little blue-green daggers under the end represent the supports from which we will shake this beam. You cannot really easily see the mass, the 1,000-pound mass, but it is there in this particular simulation program called ANSYS. Point masses are little tiny asterisks, and they are there. There's two of them on that beam, just so we didn't load it lopsidedly. And we have placed the two resistors, one resistor to gather current from each layer. Each one has its own resistor. So that's our setup. Let's see what we can find out with it. So here's what happens when we shake the beam. We shake the beam. Because of the weight in the center, the beam flexes. That creates a strain in the piezo ceramic, which in turn generates a charge on its electrodes. The charge flows through the resistors that we put there because they are the only available path for it. And then electrical power dissipates as heat in the resistor, but that electrical power robs some of the vibrational energy from the beam, and it will damp down the vibrational amplitude. So what can we find out about this damping? Well, to find out about the damping first, let's look at the case where there isn't any damping. Let's look for what frequency this beam likes to vibrate at, or you could say, what is its fundamental resonance, the lowest resonant frequency of this beam with the mass in the middle that's supported from the end. Where is that? Where does it go wild? Well, we can take a quick scan of light vibrations that we're putting in at those endpoints and watch for when the center of the beam starts to have a significant vibration level. So using the finite element tool, we take a quick scan of base excitation, and it shows that there is a peak amplitude of vibration at the center of the beam at a frequency of about 37 hertz. I bet you didn't know that. So this is where we start building up our intuition. 37 hertz, well, you can imagine that. The beam, 1 meter long, 10 centimeters square, 1,000 pounds is a lot of weight. And just as a side note, for those of you who are already familiar with finite element analysis, in piezo world, a scan like this, called a harmonic analysis, is really a lot more useful than a search for vibrational modes, which is a popular method of quick analysis. It takes a little bit more time, but the reason it's superior is there are a lot more vibrational modes than there are modes which generate charge. And we don't care about the other ones if they don't generate any charge. So if you want to find what is aligned to electrical output from piezoelectric devices, you're better off making a scan. So getting a little bit more quantitative, let's look at what happens to this beam when we still don't have any resistors on it, but we're just watching it vibrating there at 37 hertz. And we're putting in a very small excitation. So just because the beam dimensions are in metric, at the ends of these beams, we're only rising and lowering the ends by 1/4 of a millimeter. That's 10,000ths of an inch for you Englishmen. 1/4 of a millimeter, 0.010 inches. It's not much. And we get to that resonant frequency zone, 37 hertz, and that 1/4 of a millimeter gets multiplied to plus and minus 18 millimeters at the center of that beam. Oh, that is a very visible vibrational amplitude. And that's typical. The resonant amplitude of something is enormous compared to the excitation that happens. So with no resistors in place, we got a resonant response of 18 millimeters to an input of only 1/4 of a millimeter. And that's kind of phenomenal, but that's how you build up your intuition. Now,
that was easy.
Who put that in here? Yeah, well, okay, so I guess that part was easy, but just hang on, because we can find out some more from this model. And this is the easy part is over. And now we get to some perhaps counterintuitive conclusions. Interesting counterintuitive conclusions, which will build your intuition up. So we're going to introduce the resistors into the situation. So we vibrated the beam, and we saw that it has a plus and minus 18 millimeter motion with the weight on it, but no resistors. So we start adding some resistance in. And so here you see a graph with some actual values of resistors that we'd add. Now remember, there's one of these resistors for each layer. So as we start adding the resistors in, we see right off the beam that they affect the resonant frequency. The more you load it down, the higher the current draw, and the lower the resonant frequency drifts. So you look at this graph, and I'm just going to take my specs off and look at it with my bionic eyes. You see, it doesn't really shift that much. You say, okay, so down at the lower end, when we have a little bitty resistance or a low resistance, we have like 35.5 hertz, and then way up there when there's really high resistance, like 100 kiloohms or so, we get like 36.5, getting close to 37 in the limit. He's like, that's really not much of a frequency shift, but when you think about there's a 1,000-pound mass vibrating on that beam, sticking in 2 little bitty resistors like that and getting that big an effect, that is pretty amazing. Pretty amazing. So we go back to the finite element analysis, and we examine another aspect of its output. And we find out that for the trouble of shaking that beam, that 0.25 millimeters at each end at resonance, we can get 3,000 watts out of that. And that when that wattage is extracted, the vibrational amplitude, that plus and minus 18 millimeters that we did see when there was no resistance, drops down 70%, close to 70%. And furthermore, that it isn't true that we can put any old resistor in that path and get this result. If you look at this graph, you see there is a minimum, there's an optimum resistor that gives you the minimum vibrational amplitude on that beam, that or the maximum reduction. And in this intuition booster example, it's 60,000 ohms. If you're an engineer, by now you've got some pretty serious questions about this presentation. Maybe the top one would be, look, buddy, you got 5-centimeter thick plates of piezo there, and you're putting some pretty good stress on them. How high a voltage are you getting out? And the answer is, well, it's between 12 and 13,000 volts. I did say it was an outrageous example. You could say, other questions? How critical is that damping resistor value? Do I got to get that exactly right? And what about the bandwidth? It looks kind of narrow. Can you do any better? Can we get it wider? And what happens when you put random vibration in instead of your nice sinusoid there that you have in that example? And another thing, are you overstressing that piezo? We'll get to as many of these questions as we can in the rest of the talk. I'll say something about choice of components and bandwidth achievability. If you notice those earlier graphs we showed, the damping resistor value is not terribly critical. You could use between 50 and 100,000 ohm resistor and not really have much change in the damping effect. However, the bandwidth that you get is only 2 hertz out of that 37. That's really pretty narrow. That's not even plus and minus. That's about plus or minus 5%, not even. So if you're going this simple route with a resistor damper, that's pretty much it for any normal structure. Anything that's got a fairly high Q, such as we showed there. Not a lot of other damping losses besides the structure itself. For resonant systems like this, and you still want passive electronics, there is a way to widen the bandwidth by a factor of 2 or more, maybe 3, by using something called the series resistor inductor scheme, wherein you, instead of just the one resistor, you have a resistor in series with an inductor, and that can be either a real inductor or one that is made up of circuitry that simulates what an inductor does at the expense of some externally input electrical power. Both of those methods can widen the percentage of damping and bandwidth considerably. You can actually achieve better damping performance than the pure resistor, and you can also get a wider bandwidth. For broadband systems, if you really want broadband, that is beyond plus or minus 5%, you would have to move on to something that we call active control, which isn't technically damping. In those cases, which do exist out there in the industry, most notably probably in hard drives, they are used using a scheme of sensing the vibration by some means, could be another piezo or it could be an accelerometer, and then using that information with some smarts, either analog smarts or digital computer smarts, to create a counter signal that is applied to some piezo actuator, which is either touching the bar that's resonating or is laminated directly to it. And that applied voltage to that piezo is done at in a direction and a magnitude that counteracts the external influence. And using this kind of scheme, the bandwidth can be quite broad, typically an octave or so. So those are the ranges which we can expect to get to using component choices or electronic schemes. Well, what about non-resonant systems when the frequency goes down to nearly zero, like we might expect to use for a hydraulic system or something with a magnetic actuator? Sometime we're like non-harmonically stressing the ceramic. Is there any way to use that, or how does the piezo stack up in that kind of situation? Well, here's a way to think about it. In this particular example, we use something called a bimorph structure, and we use the material called PZT5H, which is common. And we used it in what's called the 3-1 or transverse compression mode. When the beam bends, the stresses the significant stresses are along the long axis of the beam, but the polarization of the beam is through the thickness, the 5 centimeter thickness. And in that mode of use, the piezo on a quasi-static compression can only collect about 20% of the energy that's put in mechanically. Not real high, not zero. So that's one answer, is if it's a non-resonant system, you can collect about 20% of the energy that is put into the ceramic itself. Most of the time, we don't build things out of pure piezo like this example. The piezo is applied to some structure that has got a lot more uses and is stronger and is able to effect what it is that we're trying to do. So that 20% is not 20% of the vibrational energy or the flexure structure of the whole system. It's 20% of the energy that gets into the piezo because of the flexing. So that gets you down. Now you're down into less, like maybe 10% or 5% of the total. Still might be enough, and you can do that at any frequency that you can apply voltage. The bimorph is the way we usually use ceramic for a bending element, and it usually does have a polarization as we described, where through the thickness of the part. And however, one could construct either bimorphs or other structures that utilize what's called the 3-3 mode, where the compression is actually along the axis of polarization. So in order to do that in this example, we would have to polarize that beam the long way. That becomes extremely difficult, considering when you polarize something, you might want to apply 50, maybe 100 volts for every thousandth of an inch that you go for that entire meter. So that you can see the difficulty in doing that. This can be overcome by putting electrodes at reasonable distances and wiring things up in series and parallel, so that you maybe only need 50 or 60,000 volts, which can be achieved. And you get a kind of loop-de-loop polarization pattern, but for the most part, it's along the length of the beam. And for your trouble, you have a higher energy density. You get the almost a 3-3 mode energy density, but in a bending type element. You could also consider other structures entirely that aren't bending beams, where you have a stack of piezo layers you can of convenient thickness. You can wire them up in parallel, easily polarized, easily stacked, wired in parallel, put in the structure, get a pretty high energy density with that. You can get with a 3-3 mode, pure 3-3 mode, for that same ceramic that we use in our example, you get 56% of the compression energy can be converted to electrical energy, and that's quasi-static. So that's pretty good. Again, that's 56% of the energy of compression that goes into the ceramic and not for the rest of the structure. But I think you can see the advantages of that, and there are many devices out in the world that use this scheme. They don't look like our example, and too many to cover here, but perhaps a later talk. Oh, some guy in the back there that was asking about overstress. Overstress is one of the most important things to consider when you're doing piezo design work, particularly this. So let's talk about that. The easiest way to gauge punishment for piezoceramic designs is to estimate the maximum surface strain that will occur anywhere on the piezo part of the structure. And a good rule of thumb to follow is when you're designing something that's going to see repetitive stress is to try to keep the surface strain below 500 times 10 to the minus 6 meter per meter, inches per inch, centimeter per centimeter for all operation. This is a rule of thumb. It can be transgressed, but with great care. So let's look at our example. First, we look at when there is just having the weight on the beam. So it's 1,000 pounds, and you got this long beam, and so that's probably pretty bad. So we take 1,000 pounds and we put it on the middle of the beam, and we look into the finite element model, and it says, "Hey, that's great. We got a comfortable 148 microstrains." Okay, so now let's put in that tiny amount of vibration at the end. That's, remember, 1/4 of a millimeter at the end, plus and minus 1/4 of a millimeter. Well, we find out when that thing gets resonating and it's moving that 18 millimeters, well, the dynamic stress, worst case for the beam in the center, works out to be 3,400 microstrains. And if we actually did that, that beam would just blow apart. Ouch. However, if you're going to address this as an engineer, this is a suggested path. You could say, well, let me see. I'm looking at my finite result here on the screen, and I see, yeah, okay, it's 3,400 microstrains, but it's just that little bright red and bright blue spot on the screen in the middle of the beam. What's going on with the rest of that material? Well, that's one of the bad things about this example. It's just really poor use of material. You got an awful lot of piezo in there, and you got this little bit in the middle that's taking this heavy strain, and it's going to limit the performance. The only thing that really counts as far as damping is average strain. But when you look at this beam, first of all, near the center line of the beam, there's no stress at all. Near the outer fiber, it's high stress. If you average that out, that's a factor of 2 down. Also, there's no stress to speak of at the ends of the beam, but near the middle it's the max. That's also a linear distribution. So that's another factor of 2. So overall, we aren't really getting close to 1/4 of what this beam could do in the way of damping, just based on the average strain and this configuration. So if we were to redistribute this stress, and I'm not explaining how to do that now, I'll leave that up to you, but if we redistributed it, we could drop that 3,400 down to 850 microstrains or so. That's the factor of 4 business. So that's getting much closer to 500. In fact, there are some applications where you could stand 850. However, in case we don't want to go that far, or in case doesn't apply, there's one more trick that can be used, particularly, well, actually it can be used with either benders or with stacks of ceramic. And that is to put this ceramic in its original state before we stress it in any way in the application. We want to put it in pre-compression. So in the terms of this beam, you would make it like a pre-stressed concrete pole where there is some metal element that goes right through the whole thing and applies tension to the ends. For a lot of bimorphs that are sold, now I'm not talking about this size, but the little thin ones, they're maybe 20 thousandths, a half a millimeter thick and 2.5 centimeters long. Those have a metal shim layer right down the middle, and typically they are assembled at elevated voltage, and the thermal expansion of that metal layer is higher than the ceramic itself. So when it's assembled at high temperature and the bonding cures and it takes out of the oven and it comes back down to room temperature, there is a little bit of precompression on the long axis of the beam. And that means that when the thing is bending, it will endure what appears to be higher than 500 microstrains, and it will still have the infinite lifetime that we all know and love. So, in fact, you could actually get the kind of performance we're talking about, 3 kilowatts, out of this volume of ceramic, but you would have to rearrange it into some other form and make the use of the ceramic more efficient. Okay, just to summarize what we found out so far in another way, we have this example that works at 36 hertz. The power per unit volume that we get out of this is the electrical power that we get per unit volume from the piezo, is 0.3 watts per cubic centimeter. And the power per weight is 40 watts per kilogram. Neither of these is anything to write home about in mechanical engineering world. However, in any application that's not married to 36 hertz, you could get more than that. Power density that's extractable from piezoceramic elements is directly proportional to the frequency of applied stress. If you have an application that's not 36 hertz, maybe it's between 300 and 400, you'll get 10x of these numbers. If you have an application that perhaps could go to 20 kilohertz, you can get more kilowatts per pound out of a piece of ceramic than you can get out of any magnetic generator. Now, to help us think about this, we prepared a nomogram that we can look at in the next slide. I found it really useful when I'm considering new applications for damping or piezo harvesters to make up one of these nomograms. This particular one is not for our application. It's for a very small piece of ceramic, 10 millimeters by 10 millimeters. And it is only 1/4 of a millimeter thick. Sorry, yes, 1/4 of a millimeter thick. It's the same material that we did use in our example. So this nomogram, on the vertical axis, it has the strain that you're giving to the ceramic. And on the horizontal axis, you have the frequency of application of that strain. So all these are dynamic dynamic situations. So you can see if you go on the frequency axis, you go lower and lower and lower, you have to really jack up the strain to maintain the same constant output. So here at 150 microstrains and 200 hertz, the thing is not even sweating, and you can get 2 milli. I'm looking at the lowest curve there, the 2 milliwatts of power out. By the time you get below 50 hertz, you're at the limit of the ceramic to get the 2 milliwatts. So this is the game. The strain is a square law. The relationship between power output and strain amplitude is a square law. So double the strain, you quadruple the amount of power you can get out. The power that you get out depends on frequency only linearly. So when you double the frequency, you double the power out. And the trade-off in every application looks just like this graph. So, in all cases, you're better off at high frequency, but sometimes you won't be working there. And so you can see what kind of window and trade-off in material volume and so on that you need in order to maintain the output power that you need to do damping or anything else for that matter. So, in conclusion, I would like to summarize the damnedest damper design challenge for mechanical engineers that are looking forward to using ceramics, piezoceramics for electrical damping of mechanical vibrations. And this may sound a little like a platitude, but let me give you a little background. You have a mechanical load here. Sorry. It's like looking in a mirror. So mechanical load is at one end, the piezo is at the other end, and you have what amounts to a transmission in between the two. Now we all know what piezo looks like, and you usually have some idea what your application load looks like. And when you start off, you really don't know what the coupling scheme is, except that you know that it's going to be a material coupling, not action at a distance. So the challenge is really to erect a structure that couples the vibrational load to the piezo in such a way that the ceramic is uniformly stressed. It's not easy, not as easy as it sounds. Things don't always want to come out uniformly stressed. You have to do some spreading in the meantime. And you also want to operate at the highest possible frequency so that the ceramic is fully utilized and it has the highest damping power. You could contemplate structures which create vibrational stresses at the ceramic site, which are actually higher than the vibrational stresses at the beginning end at your application. This is not unthinkable. And so I don't want you to think that you just take this piezo brick and whatever, I'm going to work at 500 hertz and I've got to go through and do this deductive thing. It's not deductive at all. And there have been some very, very clever schemes for adapting a particular load to a piece of piezo. And normally they're erected, those imaginative schemes are erected because of various limitations, space, weight, cost, etc. So the challenge is to think up that transmission that's in the middle between the load and the piezo and succeed at doing damping. So I wish you good luck. Thanks for listening to our presentation on the outrageous piezo damping example. And if you have any questions, please feel free to reach out to us at piezo.com. Bye for now.